Okay, here we're going to talk about rates of chemical reactions. Alright, now let's start off with an analogy to the word rate. Okay, when you drive your car down the street, you're going to be following the speed limit, which is usually in miles per hour, at least if you're driving in the USA. So, when you drive your car, you're driving it according to the posted miles per hour speed limit. Alright? So how does somebody know whether you're going that speed or not? Or how does somebody know what speed you're going? Well, they'll hold up this cone-shaped device that will figure out what your speed is, like a lot of cops have. And the way those work is by measuring two things. Alright? When the cop measures your speed, what he's able to do with that unit is measure the change in distance that you've gone. And that's usually in miles, even though of course you haven't driven 1 mile when he's just tracking you. And then over the change in time. Alright? In miles per hour at least, that time is hours. Alright? So all speed is just change in distance over change in time. And if you represent distance by x and time by t, you can say that's essentially what you're talking about. Alright? Change in distance over change in time. Well, chemical reactions are actually really kind of similar. The only main difference is that you're not measuring change in distance over time, you're measuring something else, and you're usually measuring change in concentration. So when you talk about the rate of a reaction, you are talking about the change in the concentration of whatever species you are measuring over the change in time. Alright? These square brackets here, just shorthand for the word concentration. Just makes it easier than writing out the word concentration every time. So like I said, you aren't measuring distance, you're measuring concentration change. Alright, and that's really what the rate of a chemical reaction is. Alright, so let's actually look at an example. Let's look at the reaction between hydrogen gas and iodine gas to give hydrogen iodide. You always want to make sure whenever you're dealing with something like this, or indeed whenever you're dealing with a chemical reaction, that it's balanced. You know, we put that 2 there, so it's balanced. If the 2 wasn't there, for reasons we'll get into in a bit, your data would be all messed up. So if I was to try and figure out, well, what's the rate of the reaction with respect to this hydrogen? Alright. In theory, I should be able to generate the reaction rate from this, and from this. And, in the same respect, the rate should be the same regardless of what I'm looking at. Alright. The analogy there being, it doesn't matter whether the cop has his gun pointing behind you, not his gun, his speedy measurer thingy, the technical term for it. Whether he's behind you or in front of you or the left of you or the right of you, it doesn't matter. What his point of view is, he should be able to get the same information, and it's exactly the same here. It doesn't matter whether you're looking at the reagents or the products, the rate should be the same either way. It would be kind of weird if you had a different rate here to this rate. Okay? So, let's see if we can figure out a way to classify, a way to determine the rate with respect to the hydrogen here, and I'll show you what this is. So we're talking about the rate is going to be equal to the change in concentration of my hydrogen, just like so, over the change in time. Alright? Now I'm going to put something here, I'm going to put a negative sign here. And you might be wondering, well, why are you putting a negative sign there? Well, the reason why I'm putting a negative sign here is because what happens to the concentration of your reactants over the course of the reaction? Well, if these are your reactants, the concentration is going to go like this. Alright, concentration is just going to decrease. Because that concentration is decreasing, that is the reason for putting the negative sign here. Alright? So whenever you're talking about the rate of a reaction with respect to a reactant, there's always going to be a negative sign there. Whenever you're talking about the rate of a reaction with respect to a product, there's always going to be a positive sign there, because in here the concentration is going to increase and not decrease. Alright? Does that make sense? I hope so. Alright, so let's just carry on and figure out what this actually means. So how do we actually calculate this change in concentration? Well, change in anything, like you've seen before, is always final minus initial, and so that's exactly what we would apply here. If we were going to say, well, I want to figure out the change in this concentration, or if I want to figure out the rate from, say, from time t1 to time t2, whatever those times might be, my change in concentration is going to be, I'll put my negative sign there, is going to be, oh, hang on, that shouldn't be there, is going to be that concentration at my final time, which in this case is time t2, minus the same concentration, or the concentration of the same species, at time t1. The times, of course, are going to be t2 minus t1. A lot of times you'll see that t1 is 0 because it's asking, the rate will be asking about from the start to this point. But that's the formula to figure out the rate of a reaction with respect to a product, with respect to a reactant, by the way. Now, what if I was to do the same thing for the product? The one product here being our HI. Well, we've got our delta sign, we've got our HI, and we have our time. But there's there are two more things I have to put into place. One of them is the plus. Notice I've left some space here, and you'll see why that is, well, right now. Look at the molar ratio of my species here in the balanced equation. 1 to 1 to 2. What this means is, for every 1 mole of H2 that gets used up, 2 moles of HI form. In theory, that means this is forming twice as fast as this is being used up, which, if I was to figure out the rate of this compared to this, I'd then see that this is twice as big. And if I want my two rates to be the same, then I've got to make sure I include some factor to take into account that factor of 2 here. So what I do is I take that 2 and I put it on the bottom here. So that 1/2 takes into account the fact that this rate would otherwise be twice as high as this rate. And like I was saying before, you have to make sure the rates are constant all the way through. Alright? And then I can take this and show it just like this. Alright? In this case it will be plus 1/2 the concentration of my HI at time t2 minus the concentration of HI at time t1. And if t1 is the start of the reaction, this is probably 0. Again, all over t2 minus t1. So it's important to remember a couple of things. Not only the sign here that goes at the start, but also whether or not you would need this fraction here. If this were 3, this would be forming 3 times as fast, and I'll have to multiply this by 1/3. If it was 4, it would be 1/4. Okay? Hopefully that makes a little bit of sense. Alright, now before we go on, let's make sure to clarify one thing. Just before I was talking about the rates of reaction. We want all these rates to be the same. Okay? That's not the same as when you talk about the rate of formation of this, or the rate of loss of this. Then those are different because this is forming twice as fast as this is being used up, so those rates would be different. Okay? So when you're talking about the rate of the reaction, just as we were talking about here, where everything's got to be the same, that is not the same as when we talk about rate of loss of product. Oh crap, not loss. Sorry, formation. Or rate of loss of reactant. So just make sure you understand the difference there. If the question asks you about the rate of the reaction, then you need to include these fractions. All right. If you talk about the rate of loss or rate of formation of product, you can actually start with this, and I'll show you how to manipulate it where this gets taken into account a different way. All right, let's actually look at an example. Let's say the reaction of H2O2, so hydrogen peroxide, with I minus, that should be 3I minus, and this is an equation I'm just writing down here, and this isn't necessarily one I want you to know, but I want you to know exactly what we are doing here once I finish writing this out. So the two products that we get this funky guy, which is I3 minus with a single charge of -1, plus 2 molecules of water, of liquid water here. All right. And then a little bit of information. In the first 10 seconds of the reaction, the concentration of iodine dropped, as you would expect, because iodine is a reagent, dropped from 1.00 molar to 0.868 molar. Alright, so that's the information that we have. And the first question that we have to answer is calculate the average rate of the reaction in this time period. Alright, we can't do it for any other time period because we have no other time or concentration data. So this is what we can do. And one thing that I'd like to do is just to apply what we were talking about here with respect to this reaction here. So notice it's saying the average rate of reaction. It's not talking about the rate of loss or gain of reactants or products. So what we'll start off first is we'll say that the rate of the reaction is, first off, it's going to be equivalent to the rate of loss of my H2O2 over the change in time. Or it's going to be equivalent to the rate of loss of my iodine. Because this iodine is being used up 3 times as fast as the H2O2, I have to include the 1/3 coefficient here, just as we were talking about before, again over the change in time. And that rate is also equal to the rate of loss of this hydrogen, and because this coefficient is 2 here, this is going to end up being 1/2 my concentration of H plus over time, over a change in time. And then we get to our products, where our signs here become positive. Alright, because the coefficient for the I3 minus is 1, I need nothing else for this other than the change in concentration of that over the change in time. And I could also do something for water here, but why do you think I don't include anything for the water? Well, the reason for that is actually quite simple. Water is a pure liquid, it has no concentration, so we can't measure it. So therefore the rate is equal to all these. So if we had information on changing concentrations of H2O2, H plus and I3 minus over this time period, in theory we would get the same rate as this one. Alright, but let's see what we can do. The rate of reaction with respect to the iodine is simply this. So that's what we're going to use. Alright, so we're going to say that the rate is equivalent to this over time, over the change in time, which means we have our negative 1/3 times our final minus our initial concentration. So we have our 0.868 molar minus our 1.00 molar, 10 It says in the first 10 seconds of the reaction. So what's my initial time? Of course, it's 0. All right. So 10 seconds, and this is molarity here, or moles per liter. And when you multiply all that out, 1/3 times this divided by this, what you get is a value of 4.40 times 10 to the minus third moles per liter per second. And like I said before, if I had the concentration change data for this, and this, with these coefficients in place, I get the same rate no matter whether I'm looking at the reactant or the product. Alright, one last thing. Can we predict what the rate of change in the H+ ion concentration is during this time period? Can we predict that? Well, actually, yes, we can. We don't have any concentration data for the hydrogen. This time period means the same time period. Because we don't have any concentration data for this, it's actually not important because we have the rate. Alright? So we know that this rate is equal to this one, is equal to this one, is equal to this one, is equal to this one. Alright? So the rate is not the same as the change in concentration of H+. And I'll show you exactly why. Because we know that the rate of this reaction, which is 4.40 times 10 to the minus third moles per liter per second, is equal to what we said here, -1/2 of the change in hydrogen ion concentration over the change in time. Alright? And if I want to figure out the rate of change of my hydrogen, I want to figure out essentially this. And if I want to figure out that, that means I've got to do something with this. I've got to take it over here. So therefore the 2 goes up to the top. So therefore what that means is the rate of change of my hydrogen ion concentration is 2 times 4.40 times 10 to the -3 moles per liter per second, or 8.80 times 10 to the -3 moles per liter per second. Now let's just check if that actually does make sense. If my iodine, let's see, if my iodine is, or if the rate of my reaction is 4.40 times 10 to the -3 moles per liter per second, that is, for example, the rate at which my hydrogen peroxide is being used up, because I have no coefficients here. The rate of my H+ ion being used up should be twice as fast because of the fact that here I have a ratio of 2 to 1. Alright? So if this is being used up at a rate of 1 mole per liter per second, this should be used up at a rate of 2 mole per liter per second. We've already figured out that the rate of this being used up is the rate of the reaction, which is 4.40 times 10 to the -3 moles per liter per second. And so therefore that for the hydrogen ion should be twice that. And that is exactly what we find. If we would do the same thing for the iodine, then we'd find that it would be 3 times this, which would be, what is that, 1.32 to the -2 or something like that. Anyway, that is pretty much everything I wanted to go through about rates of chemical reactions, taking into account the coefficients here and the signs, and then how to figure out relative changes of concentration of particular species. Alright, thank you.